In today's video, we're going to be talking about something called a voltage divider. Really, this just follows from what we've already learned about resistors in series. One of the benefits of using the voltage division principle, though, is that it can simplify our analysis of circuits if we can recognize that we have a voltage divider to be dealing with. Let's take a look at what a voltage divider is, what it means to divide voltage, and how we can use it to our advantage. Here's a circuit that has a power source and two resistors in series. For simplicity, I'm going to make them both 1 ohm resistors, and that's a 10 volt power supply. Now, we know that these two resistors share a current I. What we don't necessarily know is what the voltage is across each resistor. But here's where this might be relevant. If I were to take these two terminals out and call this one VD for V divided, I might want to see how does VD relate to our 10 volt input. This is one way where we can make a voltage source. Now, it's important to note that voltage dividers aren't particularly good voltage sources. However, the setup here, where we have two resistors or more in series, and where we were interested in the voltage across each of them, is quite common. And it's actually used many ways to either read a sensor or to provide a known voltage. So the question is, what is VD? Well, if we take a look, VD is going to be 1 ohm multiplied by the current, I. But what is the current? We can use what we know about series resistors. From series resistors, R equivalent is equal to 1 plus 1, or 2 ohms. The current then is going to be equal to 10 volts divided by the equivalent resistance 2 ohms, or 5 amps. I can now plug this back in here and see that VD is 1 ohm times 5 amps, or 5 volts. This is where we get to the name voltage divider. 5 volts is 10 volts over 2. In this particular case, we've divided the original voltage by 2. But can we do different ways of division? Can we do, for example, 2/3 of the voltage? In fact, we can. Rather than dealing with known resistors, let's call them R1 and R2, and let's redo our analysis and see what we end up with for VD. So, doing everything as generically as I can, I just have a voltage source V. Typically we call this Vin, or the input voltage. And then I have my two resistors, R1 and R2. I still have the current I, and I'm interested in this which we're calling VD, V divided. From a similar analysis, again using Ohm's law, we know that VD must be I times R2. I, in the exact same way above, is going to equal to our Vn divided by the sum of our resistors, R1 plus R2. So, subbing this back in there, what I end up with is VD is equal to Vn times R2 over R1 plus R2. Normally the way we write this instead is to put Vn at the end. So, that should be a 2. Depending on the values of R2 and R1, we get different fractions. Let's take a look. I'm going to keep this equation up here, and I'm going to say now Vn is 9 volts, and I'm just choosing numbers randomly. Why don't we say this is 2 and this is 3? So the question is, what is VD? I don't need to redo the analysis because I already know all my values. VD is equal to 3, that's R2, over the sum of the resistors, 2 plus 3 is 5, times Vn, which is 9 volts. Or, in this case, 27 over 5 volts. Now, the voltage division principle on its own is very useful because we might come to a circuit where we have a similar setup to a voltage divider. Let's take a look. Let's say that I have a voltage source, and then I have some unknown element here, E. If I want to know what the voltage is, I could use the voltage division principle. I won't need to reanalyze the entire circuit. Notice one important thing though. If this is a resistor, then I need to compute R2 as the parallel connection of my two resistors. This is one of the reasons I said it's not a particularly good voltage source, because depending on how you load it, the voltage will change. But as long as you know how you're loading it, you can compute the voltage knowing the voltage division principle. Now you might ask the question, well, what if I have more than two resistors? Could I do a voltage divider on all of them? And the answer is yes. Let's take a look at what happens when I have more than one resistor. And I'm going to do this generically. Again, this is Vn. And we'll be using 3 resistors only because it's easier to draw, but this will work for no matter how many resistors we have. There's resistor 1, resistor 2, and resistor 3. And let's just say that I'm curious about the voltage here across R2. I'll call that one V2 now. Well, the analysis is the same. I know that V2 is going to equal to the current I times R2. And the current I is still going to be the voltage in divided by the sum of the resistors. In this case, there are 3. So at the end of the day, I get that V2 is equal to, and again I'm going to be putting V in at the end, R2 over R1 plus R2 plus R3 times Vn. I can do this generically. At this point, the diagram is going to get a bit messy. This is R1. Then there's an R2 that should be connected. And then these 3 dots means a bunch more resistors connected. I don't actually know how many. And then Rn. And in here, I'm curious about Vi, which is the voltage across the ith resistor. Well, my analysis will be the same, won't it? Vi, there's going to be a current there, let's make sure that's in there, is going to equal to current times Ri. And the current is going to be Vn over now the sum of all of my resistors. Let's use J, just so we don't confuse things. So, substituting it back in is equal to Ri over the sum of all the resistors times Vn. You can use this to simplify your analysis of circuits. Once you recognize there's a voltage division going on, you don't need to redo all of the analysis for every single resistor. You just use the voltage division principle once.